Some key example of the version for calculating well-test uncertainties, not with the fundamental example and not with the advanced example, but with the hyper-advanced version, shall I say. And you can see this one is way more elaborate because, for example, the number of inputs has exploded. You have matrix porosity, reservoir thickness, Weber radius, and all of the input data on the left. And you have a lot of parameters you can choose from in model selection. So you don't have only errors from input data, such that are called here basic data, but you could relate to as static data. They are preliminary. They're sort of preliminary knowledge to knowledge about well-test results, and you can eventually get them from your logs when it comes to porosity, or for sampling when it comes from oil viscosity or volume factor, or total compressibility, or from errors on your production rate. On the other hand, the one on the right hand section, they are more related to the fluid that is measured, and they are specific of the match, of the quality of the match, and the error you get on the match, usually calculated by least square method. It's not necessarily the best method, but it's the one very commonly used in most well testing analysis packages. So to show you how it works, so to summarize, this hyper advanced version, it has not only a generic, something better than a generic well-test uncertainty on the output based on many cases. It doesn't have only the same generic error produced as a probability density function using a normal function. No, it goes much further. It takes all the input from static data, all the input from the match, and actually this is the error on the model selection, and very few conventional software packages do that, and if they do it on other elements, and this comes not as a competition to existing software packages, but as an add-on. So when you produce your well-test results, you can run this as a post-processor. It doesn't affect or alter the quality of your match, but actually it displays the error, it reintegrates the error, and produces a final result at the end, combining the error from both the model selection and the static data. So to show you an example, we can look at matrix porosity. We can choose different probability density functions. You can choose normal function, triangular. There are some rule of thumbs that we can explain during the support process. And then you select your high value, low value, and the peak value at which you have your peak for the triangular. You can do the same with the normal function. You can select and you can choose the mean and the standard deviation, and each box is adapted to the sort of input required. So uniform, you get a high and a low value. So each of them is adapted. But this is if you want to go a bit away from the common rules that we will suggest and recommend on each static parameters. So it gives you flexibility. It also allows you to choose yourself what high, low, and mean value you want to have, and instead of using necessarily our guidelines. Although we recommend usually strongly our guidelines, there are always exceptions or cases where you know better or have a more refined definition for any strong reason. So that's for the static data. if we shift to the model selection, the good thing it's split between early times, middle times, and late times. So you can choose all the combinations of model from early times and middle time and late times in your well testing. So you can select wellbore storage and skin, and you will be asked to provide the high and low value on each of the match parameter. So CD exponential to S, time match, pressure match. And you have it specified for each model. So you have match parameters that are required for initial for vertical penetration, for example HWD, ZWD, or you can have cases for infinite fracture, and you have CDF, you have match that are specific for each cases. Yes. So you have your match for fracture. You have other types, more complicated partial penetration. You can get slanted partial penetration with the theta angle and or horizontal well. So this is very refined and defined for each case. For the middle time, you can have just click OK, and you won't go further, or double porosity behavior, and you get all the match lambda exponential minus 2s, etc., and so forth. So you have really very exhaustive list of requirements, and the same for late flow. I'll let you have a look at it. So you have your distance to a fault and some caution. You have, in case you need the two distance, and you can select your probability density function the same way. Or you can just choose an infinite extent, and just like for homogeneous behavior, you will be put in a default mode. And once you get all these parameters, you can go here and click Run. And this is going to generate all the probability density function for all your input on the static data, and so the variables, and on your model selection, so on the parameters of the model. So you click Run, and once all of these are generated, it can take up to 3 seconds. You click Run for the Monte Carlo simulation, and that will provide your output results, all your margin of incertitude or of error on every output parameter. Once this is finished, you click Display Result, so it's displayed in the graph. So you have a graphic display. So to skip the time that it takes to process all this, this is usually 1 to 3 seconds, can go up to 10 seconds. Monte Carlo simulation is also takes some seconds, but it can be shorter because it's really the generating the trials that takes a lot of time. So to skip this, we can go directly to the results. And in fact here, it's not only the result, but we put in a spreadsheet the correlation using Spearman rank, so to show how the output result is correlated with different static data. So you have the influence in percentage here on the permeability. This is a specific case, and this is not mentioned here, but you can see what is the static data influence on every case. Just a reminder, if your model selection if you don't want to put an uncertainty in it because you consider that your match is quasi-perfect, you can put a single value as well. So here is an example. We have a module, an additional module that can calculate correlation of the result versus every static data input, just like you have in other packages. Now we can go to early time, and you get all the percentiles on your result. This is a modeled case, so for vertical permeability, horizontal permeability, and other parameters relative to partial penetration. You can have all the values with a lot of detail, so you'd have to cut some of the decimals here because of the precision, but you get the mean and max value, you get the average, you get the median, you get kurtosis and skewness, and all the percentiles. So that's quite great indeed. This is, for example, simulated for a double porosity milieu. So you get some of the parameters for double porosity in middle time and all the same statistics. We can proceed on to late times, and if you have a channel, for example, or a wedge, you can have distance to the faults, from your well to the faults, and all the statistics, the same stats. Now if we proceed further, we get the display. Here we have put here what's the output probability density function for horizontal permeability and all the other parameters. So that can range to different cases. You have here your conductivity and other parameters. Your horizontal permeability, that's for early times. If you shift to middle time, then you can have your match. So you can have, for example, the omega factor calculated with two different methods, omega from pressure match and omega from derivative match. And if you go to late time, we display distance to a fault, to one of the faults, and you can get the statistics and you can see where it's mostly concentrated towards low value in this case, and fading away towards higher values. So that's the total output of this type of simulation. I hope you enjoyed it, and thanks for your feedback.